Stanford University.
Thank you, Lynn. Let's see, we have the right microphone on. This is a funny title. What do I mean, nuclear power and a three-dimensional energy world? If you think about energy, you have to think about more than climate. You have to think about the economy. You have to think about national security. You had a little of this from George Shultz at his lunchtime talk. It doesn't matter how hard over you are in doing things about climate. Developing countries are not going to beggar themselves so that the climate will be right. We need to develop affordable technologies for the developing world, and we need to do it for all three reasons. Now, if you think about even here in the United States, we have absolutely failed to get any national work or any national traction on carbon dioxide reduction. But we did succeed without a murmur from the people who say climate change is a fraud in doubling the mileage for cars. So the EPA standard is going to 54 miles per gallon from today's 27, and you didn't hear a single complaint about it. Now, why didn't you? If you go to 54 miles per gallon, you're going to reduce, if I could snap my fingers and have it now, you would reduce oil imports by 6 million barrels per day. We would reduce our balance of payment deficit by $200 billion per year. We'd improve our national security because we wouldn't be so vulnerable to a cutoff. And there are all those people in Congress and around the country who think it's terrific to do all those things by improving the mileage on cars. But if you had gone to them and say, we're going to improve the mileage on cars just so we can reduce the country's total greenhouse gas emissions by 10%, you would have heard a howl, but you didn't hear a word. And so the message here, which I want to do in an introduction before I get to the nuclear issue, is to think in this broader focus. Climate only is one-dimensional. Energy is a three-dimensional force in our real world. The Department of Defense is interested in biofuels. The Department of Defense is interested in small-scale solar systems to power forward bases and all sorts of things. So think about national security, think about energy for the economy, and think about energy for climate change. And when you're thinking about it, let's see if we can make this work. There's only one equation here I have to make you suffer through. What's going to happen to energy demand in business as usual? One of my themes here is that business as usual can't go on. You can't do business as usual. Why? So take a look at that equation. That says energy is population times per capita income times energy intensity, energy per unit GDP. And if you do your algebra right, you can cancel tops and bottoms and keep this, and it says energy is equal to energy. But think of it this way, and you know the world population is going to increase to $9 billion by 2050, 10 billion by 9 billion people by 2050, 10 billion by 2100. World capita income is going up. World energy demand in business as usual has to go up to match that. Here's one of the many predictions about what's going to happen to energy demand in the business as usual case. This one's from the International Institute of Applied Systems Analysis. It uses the projections for economic growth. It uses the projections for the standard increase in efficiency. And what it says is that world demand for energy is going to double by 2050 and is going to double again by 2100. China's emissions passed us in 2009. The developed world is going to, developing world as a whole is going to pass the industrialized world in their total energy use by 2020. Business as usual, even with zero emissions in the industrialized world by 2100, would leave you with 85% of the emissions that are predicted from business as usual with this thing. So if you love doing something about climate change, you better think about how we're going to change the system for the whole world. And in thinking about it, go back again to think about the fact that their economy is very important. And if you come up with something, I don't care how good it is on greenhouse gases, if it increases the electricity cost by a factor of 4 or 5, they're just not going to do it. So what's the economic problem? This is how much of world GDP is spent on various forms of energy. You see two big peaks there. The first is the Arab oil boycott. That was done deliberately. It wasn't a thing because of a constraint in supply. But the second peak has to do with Iran and Iraq and the Gulf Wars, and it has to do with a reduction in supply by about 10%. You reduce supply by about 10%, and the price went way up. And the price went way up to drive down demand, which it did. People drove less. We had $4 a gallon gas, which we still have. That's happening. That's going to keep on going on for a while. But if you think about business as usual, think about 4 times the demand in 2100. What does that mean? Well, let's look at what we're using now. If you look at all the energy that we use in the world economy, for energy, oil is a big one, coal is next, natural gas is next. All the rest are small, relatively small. All rest after natural gas have no emissions whatsoever. So if you want to think about doing something about greenhouse gases and doing something in 3 dimensions, you have to think about what we're going to do about all of these things. So let's look at whether this supply is going to last. What does business as usual mean? This is all the coal reserves we know about in the world today. We use 7 billion tons of coal per year now. Business as usual says we're going to use 28 billion tons per year in 2100. If you integrate this thing, you will find all those reserves are gone by 2070. Now, is there more coal? Sure. Is it going to be easy to get at? No, because if it was as easy to get at as all the stuff is now, we'd already be digging it. The Chinese are importing coal from Australia. They don't have enough to expand their thing. So I'm not saying that we're going to run out of coal. I'm just saying that we're going to run out of cheap coal. What if you look at the same thing about oil? This is the OECD's projection on oil. There are more than 5 trillion barrels of oil estimated to be left in the world now. Is there more? Yes, but the more is not so easy to get at. And you can see as you go further out on that curve, the price is going up. That's the estimated cost to get it out of the ground. If you look at the Canadian tar sands, it takes about 20% of the energy content of the oil in the tar sands to get it out. It costs you about $50 or $60 per barrel to get it out. If you need oil from the tar sands, you have a base price on oil for the whole world of $70 to $80 per barrel. So is there more oil? Yes. We're not going to run out of oil, but is it going to get more expensive? Yes, it's going to get more expensive. Anybody who's looked at the climate change things has seen these curves. These curves say, what do you have to do to control the temperature rise. And if you look at business as usual, it's the red one, it goes way up. If you look at what the IPCC says about the temperature change, they talk about 4 or 5 degrees centigrade world global average. That's a lot. And if you want to do something about it, you've got to pull it down. And remember, you've got to pull it down worldwide. It doesn't do any good just to have the industrialized world go to zero emissions. So how are you going to do that? Well, you've got a few things to do. Here's all armaments in our armory. We've got 4 sectors, and we've got, what can we do about it? Transportation. Well, all of them, efficiency is going to be very important. We can be more efficient, and efficiency is good for the developing world as well as for the industrialized world. China wouldn't need to import so much coal. There wouldn't be so many defenders of Iran in the Security Council if people didn't want to be on their good side so they can get their oil. So we've got efficiency, fuel switching, and that's the arsenal. That's what we have to do. And when you think about it, well, think about what we need to do, oil and coal, 60% of total primary energy supply, 80% of emissions. That's what we've got to get out first. Now I want to do one piece of advertising because it turns out I think this is one of the most important studies being done recently. This, as far as I know, is the first system study on how to achieve the goal of an 80% below 1990 CO2 emissions in 2050, how to achieve it in California. And it looked at increasing efficiency. It looked at a context with population growth, with economic growth. It looked at electrifying transportation, all the rest of that. And it came to the conclusion that you cannot do it with renewables. You heard some of the problems in the grid if you were here in the session before the break, keeping the grid stable with highly variable things like wind is extremely difficult to do. And what this study says is that we don't have the technology to do it. It even said we do have 90% efficient carbon capture and storage. And what's the problem? If you want to think about where to put your efforts now, if you love renewables, it's we don't have zero emission energy storage to use to balance the load. The only way to balance that load now is not the fast ones that add to the frequency, but the slower variations, is to turn on natural gas power plants. And if you do that, then you get too much emissions to meet that goal. So that's an introduction, and it's why we have to think about energy in 3 dimensions, and we have to think realistically about it. Of course, if we end up in a massive war and population doesn't grow and the economy crashes, then we don't have to worry about those sorts of things, but that's not what we want to look for. Now, let me switch gears and go over to nuclear energy. Here's a chart of the world, and what you see in grayish ones are all the countries that have nuclear energy now. Right at the moment, there are about 440 nuclear plants operating. There are 60 under construction. There are more than 200 planned. And what's going to happen to this post-Fukushima? What is going to happen, in my mind, is we will see in the developing world, particularly in Asia, we will see no change in their plans for very large expansion in nuclear. And that, by the way, generates some problems that I'm going to come to in a little bit, because some of the countries that want to go nuclear do not have the educational and government infrastructure necessary to do it. Here's a partial list. And if you look down that list, United Arab Emirates, Saudi Arabia, Yemen, Egypt, Jordan, Morocco, Tunisia, Ghana, Philippines, they don't have the educational systems at the moment to train reactor operators. Some of them don't have the government systems to regulate nuclear power plants. And I'm going to come back to that because one of the key problems with Fukushima was the regulation. We're going to have to do some inventing of governance systems if we're going to make this work. So anyway, pre-Fukushima, a large expansion was expected everywhere. Typical one, we have 440, I said, running now. People talked about 1,600 operating in 2050. If we went up by that factor of 4, what you do is you double a fraction of electricity generated from nuclear. It go from a world 16% of electricity to a world 32% of electricity. Now, the latest forecasts, again coming from the OECD and the International Atomic Energy Agency, is that we're going to have something between 800 and 1,600. Their upper limit is 1,600. The estimate as far as Asia and the developing world is going, things are going to go on just as before, and who knows what's going to happen with the developed world. There are certain ironies in what's happened. Germany says they're going to phase out nuclear power. Well, this is round 3 of German phase-outs. The first phase-out was to phase out nuclear power. The second phase-out was to phase out the first phase-out. And the third phase-out now is to phase out nuclear power again. And what are they going to do to make up for it? Well, they're going to import nuclear power from France, and they're going to import coal-fired power from Poland and Czechoslovakia. And because of the way the Kyoto Treaty is written, you are charged if you're the producer, not if you're the consumer. So if they get their coal power from Poland, it doesn't go on their bill, it goes on Poland's bill. But Poland's economy crashed from 1990 and hasn't recovered yet, and they've got a lot of room under the whole thing. So we got a lot of way to go. Now, I also talked about costs, and here we got a lot of work to do. This is the Energy Modeling Forum. It's headquartered at Stanford. This is costs for the various forms of electricity based on today's prices. You see natural gas combined cycle is the cheapest, but you see very high prices for solar and for wind. Those are going to come down, but they're going to be a real impediment to doing something in the developing world. We get the prices down with all sorts of subsidies. You want to buy a solar roof for your house, you can go do it, and the government will pay half the price in effect for you. So you're getting 50% off. That's a fine deal. But if you're a developing country, you can't afford that either. Let me switch to Fukushima. That's the Fukushima Daiichi power plant after all the dust settled. They had an earthquake, a very big earthquake. The earthquake to the plant did no damage. The plant worked fine. All the emergency systems worked right. The emergency generators all turned on, and everything was fine until 50 minutes later when the tsunami hit the shores. And the tsunami wiped out all the emergency generators. The tsunami and the earthquake wiped out the roads. They wiped out the power grid, and they went into a state that's called blackout. Now, their blackout was worse than anything because they had all their generators in the basement. So it not only wiped out the generators, it wiped out the switchgear, and they had no power, and that's what led to all meltdown. This is a human error. As I said, there have been no accidents having to do with the insides of a nuclear power plant. All three, 3 Mile Island, Chernobyl, and Fukushima, have to do with what was done on the outside of the power plant. If you take Chernobyl, or let's start with 3 Mile Island. Core meltdown, very good containment, almost no radioactivity off-site. What happened? The control system didn't let the operators know that they in fact were emptying the reactor of water instead of filling it as they thought. Control system misdesigned. Chernobyl, a reactor which is known to be unstable in a certain region of its operations. They took it into that region. God knows why. Yesterday I was talking to a bunch of other experts on nuclear power, and they say that a phone recording has been covered between the control room at Chernobyl and their masters in Moscow. And the new operator coming on at midnight calls up and says to his boss in Moscow, "The instructions on this test are all crossed out in the logbook. What should I do?" And his boss says, "Go do what you would have done if it wasn't crossed out." And we lost the Chernobyl power plant. Fukushima was a failure of defense in depth. They made a mistake on how big the seawall should be. The tsunami was 45 feet high. The seawall was 20 feet high. That drowned everything. But they made another mistake. They had the emergency generators in the basement. They had a third mistake. They had no way to connect up external sources. Then they had more problems because the roads were destroyed, so you couldn't get a new generator to them. And even if you could fly it in by helicopter, which they did several days later, you couldn't hook it up. So we have a real problem in those. But I want to talk for a second here about perception versus reality. And when I do this, I start off with transportation, not electricity. I say, what's the scariest thing in transportation? Airplane crashes. Get an airplane crash, the newspaper headlines are there, all the TV channels are there, the blogosphere explodes, all the rest of that. But what's the worst hazard? Well, motorcycles, everybody knows that. But what's the second worst? Walking. Do we regulate walking? No. We certainly do have lots of things in the FAA and such to regulate transport. And why is this? Because people feel they're in control. If you're walking, you're in control, you know what you're doing, and all that sort of thing, and so you feel that hazard is perfectly controllable. Bicycles are number 3 on the list. You know, you get down to cars, you're only down to the 4th most hazardous. And again, people think they're in control, and so they are perfectly happy living with extremely risky things. Here's a story for electricity, and this is per terawatt hour. A 1,000 megawatt power plant gives you 8 terawatt hours per year. What's the worst? Oil, coal, photovoltaics. Number 3, photovoltaics, because they're very nasty things used in making photovoltaics. Gas. There's nuclear down next to the best. Wind is the best. This is done, by the way, for Europe. And I'm sorry, I thought I put the, yeah, I think the reference is on that slide. And you can find it. So it's for their pollution control requirements and so forth. So now we've got Fukushima and what's going to happen. Fukushima was and still is a serious incident. There's going to be a rethinking of reactor safety and the setting of what's called design basis threats. So every reactor has a design basis. Earthquake safety, how big an earthquake They do it in terms of ground acceleration, not in terms of magnitude, because what counts is the acceleration, not the magnitude. So there's that. There's a flood design basis. If you're close to the Missouri River or the Mississippi River, we had a close call with a flood. You got to be able to stand that. And you can go down the list. Tornadoes, they're designed to stand tornadoes. They're even designed now to stand the crash of a 747 airplane into the containment building. That's after the 9/11 thing. So what's being looked at now is multiple catastrophes at the same time. These things were looked at one at a time. And so the Fukushima thing, which is earthquake and tsunami, that's two. Suppose I had a tornado and a flood. Suppose I had an earthquake which knocked out all highways around there as well as the grid. What would I do? The other thing that's being looked at very hard is what's called station blackout. All these things are designed to be able to run with no external source of power. But the station blackout standard is 4 to 8 hours in the United States, just as it was in Japan. But the station blackout of Fukushima was 11 days, not 4 to 8 hours. That's being rethought, and it will require more fuel storage. It will require a review of how to connect external power sources and all that sort of stuff. Even so, we can say that we do know a lot about the impacts, and my personal opinion is that the worldwide impact is not going to be large, except perhaps for the United States and Western Europe. And I say perhaps because there's a lot of difference of opinion in Western Europe. France is not going to pull back from nuclear. France gets 80% of its electricity from nuclear power. France is moving toward electrification of its auto fleet, and they'll need more to charge up all the cars. Germany has done this funny business. The Swedes are doing other things, but we'll see what happens. An essential safety requirement is the independence of the regulators. The United States is the only country that has independent regulators for nuclear, but we don't have independent regulators for everything. You may remember that when we had the Gulf oil blowout and that disaster, one of the causes was what's called regulative capture. The regulators in the Department of Interior lived in the same place as the promoters of drilling. And we took a half step by leaving them in the Department of Interior, but putting them in another area so they're not in the same budget line. Why Congress had the wisdom to move the Nuclear Regulatory Commission out of the Atomic Energy Commission in 1974, I don't really know, because I wasn't paying attention to these issues. But the move out and the independence of the regulators, coupled with 3 Mile Island, which made the clout of the regulators much stronger and had the nuclear industry doing something rather remarkable, setting up the Institute of Nuclear Power Operators, known as INPO, to share information and to share best practices, and in fact to be able to fine their members if they don't do things right. Under that, the uptime for nuclear reactors went from 60% to over 90%. The regulators are happy. The utilities love this. All of a sudden, the same reactors are producing 50% more electricity. They're making a lot more money. What's happening around the world? Well, Japan just made their regulators independent. I don't know how independent they really are. India made theirs independent 2 weeks after Fukushima. China Their regulators are nominally independent, but not for real, because they're in one of the weakest ministries of the government, and it's not really good there. But to make you feel happier, the Nuclear Regulatory Commission in the US system is regarded as the gold standard of regulating nuclear power in the world. Everybody agrees to that. Spent fuel disposal. This has been a big problem, and everybody worries about it in California. There is no technical issue. We know how to dispose of the spent fuel. There have been all sorts of tests, all sorts of experiments. It can be safely put away for 1 million years, but we can't get a site to put it into. Yucca Mountain was chosen by our Congress in a top-down procedure, which took the 3 recommended sites, Texas, the state of Washington, and Nevada, and took the one with the least political muscle in Congress and gave it to them. That's not the way to do it. Most people do not know that we have a working repository. It's called the Waste Isolation Pilot Project. It's outside of Carlsbad, New Mexico. The locals are happy. The state is happy. It was done in discussion with them. They even are eager to be the site for a bigger disposal. The Blue Ribbon Commission is recommending the switch from from top down to bottom up, which is what has been done in many other countries. We'll see whether it happens. So let me give you a quick summary. The population increase and economic development are going to increase energy by a large factor by 2100. It is very important to develop what I call negative energy. That's energy efficiency. It doesn't cost you anything, but it reduces demand and does things right. In business as usual, global temperatures are going to continue to go up. The fossil fuels are going to get ever more expensive. We're going to have serious economic impacts as well as climate impacts. We need to move from fossil fuels for lots of reasons. More than just climate change, we need to do it for the economy, not just ours, but theirs as well, and for national security, because the last thing anybody wants is to be at the mercy of somebody else for all sorts of imported energy. I remind you, think about the difference between doubling the mileage standards for light vehicles and the complete lack of protest about doing it because it was an economic and national security issue. And think again, if it had been done just for climate change, you would have heard a lot about how climate change is a fraud. Wind and solar are going to be limited to something roughly of 30% of electricity unless something in GSEP is going to solve the problem of zero emission energy storage. So Sally, that's your big thing, zero emission energy storage. We need a new kind of international agreement. I didn't get time to talk about Montreal and compare to Kyoto, but I will point out that over 80% of all the emissions of greenhouse gases come from only 15 countries. We shouldn't be talking to 192 countries at a UN forum. We need to have 15 countries get together and figure out what to do. When you think about economics, this is a story I want to conclude with because I want you to think about it, even though it's going to make some of you hate me. California has a goal of 1 million solar roofs. That's one of our goals. It's supposed to reduce greenhouse gas emission. For 15% of the cost, I can eliminate 3 times as much greenhouse gas just by converting the Four Corners coal-fired power plant from coal to natural gas. Think in 3 dimensions. Think about what we can do now. Think about the fact that technology is going to evolve and we can do different things later. But please don't let us wait for the perfect and the overly expensive when we can make a big impact in all 3 dimensions with what we've already got. Thank you. I hope it's not a photovoltaic person who hates me.
It's a photovoltaic person who likes you. Could you speak about France reprocessing and also standardized reactors? Those concepts seem to work for France, reprocessing and standardized reactors.
Let me start with the standardized reactors. In the bad old days, which are the days up to now, the so-called Generation 2 reactors, almost every reactor was different. Each utility would ask for different power output and different this and this and different that. Right now, what you've got now are, I think, 3, maybe 4 designs. And nobody's going to buy anything but those designs because the people who make reactors are simply going to refuse to sell it to you. You can buy a Westinghouse AP1000, which, if I remember right, is a 1.2 gigawatt reactor. You can buy an Areva EPR, which is a 1,600 megawatt one. There's a GE Hitachi one, and there is a Korean one, which has already been sold to the United Arab Emirates. They're being standardized. Now, this whole business about reprocessing gets into an argument about the availability of fuel, and I don't think this is settled as yet. The argument for reprocessing says, look, we produced all that plutonium stuff when we were burning it. Why don't we separate it, mix it with uranium, and get 30% more stuff out of electricity, out of the original round of fuel? People who argue against it say it's too expensive, but they don't do their calculation right. It is correct that the fuel costs twice as much as once through fuel, but that is a trivial change in the price of electricity, something on the order of 5%. It really doesn't matter. A lot of the concern is that if you separate plutonium, you make available material that can be diverted to weapons production. That's an argument that's still going on. And one of the discussions looking for what's called Generation 4, we're producing Generation 3 and Generation 3 Plus now, is what's the best reactor when you consider the cost of electricity, the capital cost of a plant, the availability of fuel, the risk of reprocessing, the proliferation from enrichment or reprocessing. You go down the list, and that's a discussion that is going on, and the question really is, what priority do you put on these things? I keep asking our people, the weapons people in DOE, what's proliferation risk reduction worth? How much are you going to increase the price of electricity for it? Never mind who pays for it. Right now, by the way, for disposal of spent fuel, you pay 0.1 cents per kilowatt hour on no nuclear electricity, and there's more than $20 billion in the waste funding that's going up. So this is an issue that's quite current, and we don't have an answer yet. But at least they're asking the right questions about Generation 4.
Could you comment on the viability of thorium-based reactors, since India and Scandinavia are pursuing that quite heavily?
The thorium reactor cycle is a different reactor cycle. Thorium is not fissionable. So all thorium reactors have to be run as breeder reactors. And the system works by starting the plutonium reactors, the thorium reactors, either with highly enriched U-235 or with plutonium. And that breeds uranium-233. Now, the arguments for this is there's more thorium in the world. The arguments against this is that this is a complicated and more expensive cycle to make breeder reactors. And by the way, uranium-233 makes even nicer bombs than uranium-235. This is not a settled issue. Interestingly enough, India has been the big pusher of this because they have a lot more thorium than uranium, but they've just discovered some new uranium deposits, and their next round of reactors are going to be uranium, not thorium. Thorium is going to go into this mix of trying to sort out what generation 4 is, and I have no idea how it's going to come out. I can't hear you until you get the microphone.
In the Los Alamos Project, they discovered that plutonium left in the reactor ended up with too much plutonium-240 and other isotopes. Is that sufficient to minimize the risk?
The question is, if you get a lot of higher isotopes of plutonium in the mix, does make it bad for bombs? The answer is yes. There is even not going further than we normally do in power reactors. There's a lot more of these higher isotopes of plutonium than there is in weapons-grade plutonium. Weapons-grade plutonium comes from uranium that's been in a reactor for 3 months, and reactor-grade comes from stuff that's been in the reactor for 4 years. Quite a different isotopic mix, but here's what the weaponeers tell you. If you're talking about a nation state, they want to build bombs that they can put in their stockpile and pull them out 4 years later if they have to use them. If you're a terrorist, you don't care if you've got to put it together right now, and you don't care if it fizzles. You don't care if your 10,000-ton weapon that you set off in Washington only has 1,000 tons of explosive yield. You don't care if the people who put it together are going to die of radiation, because they're suicide bombers anyway. The concern about the risk on the back end of the fuel cycle is not from military, it's from terrorists.
One last question. Yes, would you please comment on the various forms of cold fusion that are still being investigated, like chemically assisted nuclear reaction and low energy nuclear reaction?
No, you got to ask it again because I didn't quite get it.
Yeah, there's over here at SRI and other places, there's continuing work on what used to be called cold fusion.
Ah, cold fusion. Cold fusion, cold fusion. I'll tell you a story, which is my attitude toward cold fusion. When this first started, I took a serious look at cold fusion. And when I looked hard, I couldn't see how it would work. I did some calculations and all the rest of it. So I started to get some calls from EPRI. And the EPRI guys first told me that there's a new model of how cold fusion works. So I said to them, if that's the way it works, here's what you have to do to detect the process and show that it's really cold fusion. 3 months later, I get another call, and it said there's a new model of how cold fusion works. And I went through this again. We went through 4 cycles of this before they stopped calling me. So as far as I know, cold fusion does not work, and there is no evidence that it does. And if somebody dreams up a new model, I will be happy to tell them how they should test cold fusion to see if it works, but I haven't been called recently.
Well, on that happy note, thank you very much.
For more, please visit us at stanford.edu.